Hello everyone, welcome to the Submillimeter Array on Mauna Kea. My name is Ramprasad and I'm an astronomer working at the Submillimeter Array. Let's start by taking a panoramic view of the telescopes that are on Mauna Kea. The nearest one to the SMA, in the cylindrical silvery-shaped building, is the Subaru telescope. This is a premier 8-meter class optical infrared telescope. Next to it is the Keck, one of the Keck domes. There's a second one which is right behind it. In the center now is the small dome is the IRTF. And then the white one, which is now in the center, is the Canada-France-Hawaii telescope. Then you have Gemini, which is another optical infrared telescope. And then the last two are the UH-88 and the UK infrared telescope. Mauna Kea has been a premier center for astronomy for a very long time. I would say the earliest telescopes probably started in the late 70s. Now that we have seen the panoramic view of the other telescopes, let's move on towards the submillimeter array. And as we are walking towards the array, we can see 4 of the telescopes come into view. We are actually in the midst of doing a testing and a baseline run right now. And so these telescopes are actually doing some observations. And we can slowly start to walk towards it. This is a radio telescope, and it can observe during the daytime as well. And that's what we're doing right now. We're doing some testing and daytime observations. Okay, let's stop here and talk a little bit about the telescopes themselves and the antennas. There will be a talk which will discuss some of the properties of the antennas, but each antenna is 6 meters in diameter. And you can see that it's not a solid panel, but it's actually made up of a number of smaller panels. And you have each, so you can see that these smaller panels are arranged in concentric rings. So we have 4 such rings, and where we have the panels, and there are different shapes of the individual panels that make up this entire dish. And so the total size of the dish, as I mentioned, is 6 meters in diameter. And then we can start to walk closer, and I'll show you a little bit about the optics. Okay, so let's turn and take a look at one of the other antennas. And you can see up here in the top is that, so you have, this is a telescope which is actually an altitude azimuth mount, and the whole telescope rotates around the base. And you can see that the base, which is this brown colored stone, so everything, the whole telescope actually rotates around that base. And it can then move in around the base in azimuth direction. As you can see, it's moving right now a little bit, so it's moving from one source to another, and you can see that it is moving right now. So yeah. And you can see it's really, really quiet, right? It's amazing that you can move this much and it moves so smoothly and quietly. So the tracking is actually very fast. It can move like a few degrees a second, but we typically move about a degree or so per second. And so we can move from one source to another and track very fast. Okay, so now you can see the back of the antenna. And now you can see that it was moving first in azimuth, and now it's moving up in elevation. So it's going to be tracking this source now for a few minutes before moving on to the next source. So we are running a script right now which runs through multiple sources to determine baselines and so on. The SMA has 4 possible configurations in which the antennas are located. These are the subcompact, the compact, the extended, and the very extended. We are now actually standing in front of the inner ring, and this is the home of the subcompact array configuration. In the subcompact configuration, we can stuff up to 6 antennas in this tight space. The antennas are located very near each other, and some hardware modifications need to be made to prevent them from hitting each other. Currently, we are in the compact array configuration, and we have 4 antennas located in this inner ring. The remaining antennas are actually located outside this ring, and I will pan around to show you those antennas. As you can see, we have 7 antennas in the field right now. There's the 5th one that's outside this ring, and then we will move across and shall show you the 6th one, and there's the last one, which is located in between these two. There is another antenna which is actually inside the hangar, and it is undergoing some maintenance and will join the array when that is completed. So let's go in a little bit more into this inner ring. Of course, it says that you have to watch out because antennas may move anytime, so you got to be careful when you're inside so that you're away from the antennas. Okay, so now you're able to actually see that central vertex, and so the radiation comes and hits the primary, reflects off and hits the secondary dish, which is this very small tiny dish. It's often also called a chopper, and then it bounces back and then through that hole in the middle and then actually goes inside the antenna. There's like a tube and it goes inside, and then we will show you the inside of an antenna when we go into the hangar. You also see this very small other hole that's by the side. There's actually an optical telescope, and we actually use this optical telescope if we want to do pointing after a reconfiguration. So you see right now we have these 4 antennas, and we can actually move the antennas out from one location to another. So the main thing, of course, is that you want to make sure that when you move the antennas that you disconnect everything and move it, slowly and stably. And so we have 4 possible configurations. So right now we're in this compact configuration. In a few weeks' time, we will move to the extended. We stay in the various configurations typically for about 4 to 6 weeks, and depending on the science that's available that we need to do in these configurations. So let's do a little bit more of a panoramic zoom around of various antennas. And now you can see that the Subaru telescope is in the background. You can actually see that there's snow here, right? And so it can actually snow up on top and during the winter season, winter months. And so this is something we have to watch out for, and it can be a challenge. Okay, so I'll show you now a little bit of close-up of one of the pads on which the antennas locate. And so you see that there are these 2 small tiny cones, right? And so these are the ones which we actually use to initially do a location. And when you place the antennas, you're able to get it to within, a few hundred arc seconds, or maybe even better, to about 100 arc seconds. And so once we take an antenna and put it onto a pad, we have to do a lot of things like pointing, calibration. That's the very first thing we do. And that can take typically a couple of hours because we want to get either optically a whole bunch of stars, or we can do it in radio mode and we just look at a bunch of point sources and quasars. After the pointing is done, we do the next step of the calibration, which is the baseline calibration. So we have to determine exactly how good the position is. Obviously we'll get it, we know these positions, but when you put the antenna there might be a small change, and that's what we have to determine from the baseline calibration. What we see in front right now is the transporter, and this is actually the main unit which lifts up the antenna and moves it from pad to pad. And as I mentioned, you have to actually go up to the antenna, make sure that everything is disconnected from the antenna, There's a bunch of cables, etc., power and fiber, etc. We disconnect all of those. And then you see that there's a green box on the transporter. There's actually a generator. And we can hook up the power so that the power now comes to the antenna from the generator so that we keep things cool. And then you see a bunch of hooks. And when I go up closer, I'll show you these hooks. And you should be able to see that there are actually 4 hooks. And these are the hooks that actually latch onto the antenna and will pick it up. And we have to do everything very slowly. Each move requires 4 people. We have the driver, and you can see the cab that's inside. And then we have a couple people, one in front, one in back, and another person just watching overall to make sure that all of the aspects are correct. And typically a move takes about 30 minutes or so. So pick it up, move it. If you want to go to the very extended array, etc., it might take a little bit longer. And then put it back down, make sure everything is reconnected back up. Actually, this is a design which has actually come from shipyards. I believe that ships and stuff, that's what the dockyards use to move ships. So this is a one-of-a-kind instrument, one-of-a-kind equipment, and it's actually, they don't make these anymore. For some of you who may be lucky enough to be at the ALMA site and see if an antenna moves, it is much more impressive. Obviously, the antennas are like 4 times the size. Well, twice the size, and but 4 times the size. So to be able to move those is actually amazing. And the ALMA transporter is actually completely remotely operated. No one needs to be inside the cabin. We just have like this tablet sort of device, and you can move it around. It's very impressive if you ever get there. But this is ours, and we have a few people who are trained to operate, and that's it. So it's a very moves can take typically a couple of days to move 5 or 6 antennas. Okay, so now we've seen the outside, we've seen the antennas, and we've seen the transporter, and now we are actually going into the hangar. And this is the hangar building, and you can see it's really tall because it has to actually take in the antenna. And you'll notice that the antenna just barely clears the top when we go inside. And so this is the SMA Hangar Summit facility. We have, of course, a bunch of cameras for security purposes, and now we will head inside this building. And so you can see in here, it's a little bit dark, but this is actually the antenna. And you can see that this is the antenna that's inside. And so you can see it's massive. And even though the hangar building is, seems not that big when you see from the outside, it's actually a huge building. And we can take the antenna inside. So this one is almost ready. We were actually doing a little bit of work on the antenna. It's almost ready. Everything has been tested out. And it's very, very close to being deployed. We will actually go inside this antenna, and I'll show you some of the equipment that's present inside. Of course, you have to be very safe when you go inside the antenna. And there's a ladder, so make sure that you always hold on to the ladder as you go up. Now we are about to enter the receiver cabin. In this case, we are actually about to enter the receiver cabin for antenna number 5. Okay, so let's enter, and what will we see inside the antenna cabin? And this is basically the heart of the antenna. And even before you see anything, what you will notice is this sound. The sound which goes chunk, 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 chunk. And that is the sound of the refrigeration or the cryocooling system. And this is very important because it has to cool our detector down to a temperature of 4 Kelvin. Why is that necessary? Just like you have detectors in optical wavelengths when you use CCDs, at radio and submillimeter wavelengths, the detectors that we use are called these SIS, or superconductor insulator superconductor junctions. And these function only at temperatures of about 4 Kelvin. And therefore, this refrigeration or the cryocooling system is present in order to cool everything down to this temperature. It takes a whole day to cool the antenna down to this system, and it's very finicky and it requires a lot of care. Now I will show you a little bit more about what's present inside the antenna. I'll show you a little bit of the optics, and then I will show you a little bit of the instrumentation that does the down conversion of the signal from the radio frequency, which is at RF, down to intermediate frequencies. Some of you hopefully have listened to the other talk or the other presentation and the demo on the down conversion techniques, but this is the place where all of this takes place. First, let's start a little bit with the optics. It's going to be a little bit crowded in here, so it's hard to see everything, but I'm going to walk towards the back of the antenna and show you a little bit of where the signal flow comes in. I will show you also a schematic. And up here on the top, you can see that there's a mirror out there which reflects the signal that's coming in, and then it goes through some more instrumentation which you see on the top. That's actually a calibration load, and that also does some more polarization, wave plates, and so on. So if you want to do polarization observations, that's the instrumentation that's present in the middle. And then the signal goes down, and then there's a bunch of mirrors, and there's a bunch of optics and grids, and it'll be a little bit hard to show you, but I'll try to show you some more. And you can see that there's, in the middle, there's this mirror which reflects the signal, and then if you go up a little bit, you can actually see this very fine grid-like structure that's present inside that hole. And so that grid that's present is actually a polarization selector. It can select two polarizations. The polarization that's actually parallel to those wire grid gets transmitted through and then reflected from the mirror underneath, which I was showing you. And then the polarization that's perpendicular to the wires actually gets transmitted through and then goes into the receiver itself. And you can see that the signals come through and hits this mirror. It's going to be a little bit hard to show you, and this is the mirror that it hits. And then it goes down and then hits this other mirror, and that's what I'm going to try to show you, is this. And you can see that there's a mirror in here, and then it reflects back, and there's actually a grid in the middle. It's going to be a little bit hard to see, but there's actually a grid, and that's what you see. And this grid is where the LO and the radio frequency are combined. So the signals are reflected a bunch of times, and at that place is where they're actually both traveling together. No mixing has yet taken place, but now both the LO and the sky frequency or the radio frequency travel through, and then they finally go through in here, and you can see a little bit that there's this circular window, and that's the window, and there's a filter, etc., and then it goes through that system down into the receiver itself. And the receiver itself is actually present inside where my finger is pointing. I guess it's going to be a little bit hard. So this is where the cryostat is, and it goes inside. And that's where the SIS mixer is. The local oscillator, which is this other signal that we have to generate in order to mix down, is actually present up here. And this unit that you see is actually the local oscillator. And there's a bunch of there's a numbered device that you can actually see in there. There's like a golden device. That's actually the gun oscillator, and there's a bunch of things. Come on, focus. It's now. Okay. So there's a device in there which generates the local oscillator signal, and then that signal goes through. There's a little hole which I will try to show you. And you can see that these holes, right? So these little holes in the middle are where the local oscillator comes down. So inside the rest of the antenna, you have a bunch more electronics, and then of course there are lots of computers and other things, and you can see out here, and there's a computer, and the main computer which is actually present, which does a lot of the antenna control, is this unit in here, and it's called MVME. It's obviously very different from the standard PCs and stuff. It's more of a industrial strength computer, and just to show you, just to tell you out of interest, this is actually the same processor which is on the NASA rover and the Perseverance, and it tells you that we have a very reliable unit out here. Obviously that processor is much more expensive because it's got to be space compliant, etc., and I think each of those processors costs 200,000. This one is not that expensive. And also, you might not know this, but some of you may have had the old blue, Bondi blue colored iMacs. Even those have the same PowerPC processors. And so this processor has a lot of heritage. And there's a lot of electronics in here, and you can see, for example, there's a GPS time signal out here. Then we also have the encoders, which actually measure what the position of the antenna is, etc. And then there's a lot more signal processing chains. Remember this other talk that we talked about analog to digital conversion? We have a lot more electronics in here which does the analog to digital conversion, because we want to monitor a lot of signals that are present in the antenna. And one of the things I want to finally show you in here is the temperature. And if I zoom in, it's going to be a little bit hard to see because I don't know if it's focused. Okay. I hope you'll be able to see that the temperature should be around 3.8 Kelvin in that. That's the temperature monitor. And so that's the temperature at which the SIS mixer actually operates. It's unfortunate that we can't do this live. It would be nice for you to ask questions. And you can see this is a very cramped situation. We can't have too many people in here. But if we had people who could ask questions, but you should be able to ask questions at the end of this one. So now we will actually go into the correlator room, because that's the actual heart of where all of the signals are processed. Obviously, it doesn't make sense that the antennas do set themselves, but the signals that are there from the antenna will actually come into the correlator room. So we're about to enter the correlator room. It's going to be a little bit dark, but let's turn on the light. And you'll see there's a lot of electronics in here. And the very first part that I want to show you is this particular rack of electronics. And this is actually the main analog section. So this is where all of the signals are actually generated. And you can see out here that there's a bunch of synthesizers, frequency synthesizers. You might have heard a little bit about it from the other talk. And so this is where we generate a lot of these signals, and these signals are then sent out to the antennas. So when you specify a given local oscillator frequency, there's a computer which sits and calculates what these particular frequencies should be in order to send it out. And all of these signals are not just free running, but they are locked to a fundamental reference. And our fundamental reference comes from either a GPS or a maser. And there's a 10 megahertz reference, which we know is absolutely pure. The antenna signals, which are at IF frequencies, are not sent directly to the correlator. Instead, they have to be sent over a fiber optic link. And so we have a fiber optic transmitter in each antenna, which takes the RF signal and then sends it out over a fiber optic link to this particular location. And this is the first part where the fiber optic signals which are coming from the antenna are then converted back to a radio frequency signal. And this is done with a fiber optic receiver. And the fiber optic receiver is located at the far end, and you can see in the few racks which are at the far end of the system is where the fiber optic receiver is located. And that converts it back from the fiber optic signals down to radio frequencies. Now we come to the second stage down conversion part of the system. And the second stage down conversion is done by means of what's called the block down converter. The block down converter system, which is this entire rack of units, you could see a whole bunch of these blue cables, etc. in this entire rack. The block-down converter takes the IF. You'll recall the IF is from 12 GHz bandwidth going from 4 GHz to 16 GHz and converts it back into 2 GHz chunks. And these 2 GHz chunks are then sent for further processing. And this whole unit is called the block-down converter assembly. Now we move from the analog part of the system to the digital part of the system. This is where all of the sampling and the digitization takes place. Each of these units processes 2 GHz of bandwidth. And for example, this one is called quadrant 6, and it's actually processing the 14 to 16 GHz part of the band. And inside, what you will recall is the roach. You would have seen the roach in the lab. You would have seen an open roach in the lab, but this unit is made up of 8 possible roaches. And you can see 1, 2, 3, 4, and I'll move down and you can see that there are 8 roaches. Each roach processes the 2 GHz IF from a given antenna. Each roach will do the sampling, it'll do the digitization, and then it does the Fourier transform, and then it goes to an Ethernet switch, it comes back, and then it also does the correlation as well. So this is where all of the stuff takes place. This is where all of the magic happens. It does, as I mentioned, it does the sampling, does the digitization, does the Fourier transform, and does the correlation as well. And then finally it does all of the accumulation. Because remember that when you specify an integration time, it'll accumulate the signals over that time. And then finally, once it's all done, it sends it to a main computer which is located in one of the racks. And then that's the computer which then sends it to the recording system, recording disks, etc. before you actually get the data. Finally, the last thing I want to show you is the VLBI part of the system. You will recall that the SMA is part of the VLBI EHT network and is one of the key stations which made the discovery of the M87 black hole. And now I will show you a little bit of the VLBI system, and this is actually the recorders. And what happens here is that the signals that are coming here are actually sampled and digitized and recorded really fast at a very, very high speed, because that's in these recorders the digitization and sampling is done and it's converted to a 2-bit signal. And then once the recorders are filled up and the observing run is done, we send them back to the main unit over in Haystack, where the correlation is done in post-processing. One of the things you'll see here are the color of the walls, and they're kind of red in color. And I'm going to try to zoom in a little bit to see what actually the walls look like. It's actually like a fine mesh. And do you know what this is for? This is actually a very fine copper mesh. And we use this obviously to shield this room, because you don't want any RFI signals coming in, and you also don't want to transmit any RFI signals out. And so this is a very key part of this room design. And then if you'll notice on top, you have a lot of air conditioning, vents, and so on. So this whole room has to be kept very cool and a very constant temperature. Now we will walk into the SMA control room, and this is the heart of where the telescope is actually operated, and we have operators up at the summit. Today we have 2 operators. At the far end we have Kristen. Hi Kristen. And then we have Austin. Hi Austin.
Hello. Hi.
Yeah, so I'll have Austin talk a little bit about how it is like to actually operate here.
Sure. So right now we are currently operating at 14,000 feet elevation. It's a little bit hard to breathe up here. We also have issues with weather sometimes, especially during the winter when it snows. But generally what we do on a daily basis, I like to think of ourselves kind of as the driver of the telescope, where we generally during the night shifts, we're responsible for running the proper scripts for that particular night, making sure everything's in working order, and if something breaks, we try to fix it. If we can't, we call somebody who can. During day shifts, we do what is called priming as well, which is kind of setting up and calibrating the telescopes for the night operator for that particular night, making sure everything is in working order before the actual script starts for that particular night for observing. So that's generally what we do on a daily basis.
See that this is the control. As you can see, the SMA Control Room is actually a very beautiful location because you have a great view out to the antennas and to the field, etc. And on a clear day, you should be able to see Maui as well. So I'm going to move now to Kristen, and Kristen is our very senior operator here.
Operating the telescope up here is basically no different from what we do with remote observing in Hilo. The only thing is that, as Austin said, we do have to, watch for weather up here in person. We also have to, do like physical checks on ourselves just to make sure, to check how we're doing, how we're feeling up here, because high altitude is, quite serious, and it affects people in a lot of different ways. Luckily, we do have the oxygenated room, but sometimes, like it can cause headaches or, just really weird feelings. So sometimes, in really bad cases, if we're not feeling good up here, then we can't do our jobs effectively. So we would essentially have to go down to lower elevations or even back down to Hilo. But, I think we're feeling pretty good right now. We're awake, we're caffeinated, and right now what we're doing is we are running some daytime testing. We usually inspect the antennas first before doing anything. And then, as Austin mentioned, we prime the telescope, and then what we do on weekends is we run daytime. Maybe in like half an hour or something, we'll switch over to priming the telescope for our science track tonight. And usually that consists of us just setting things up for the receivers and optimizing them and making sure everything is set for our first shift operator that comes in at 6. And that's when we head back down to Hilo, and then they stay, they remotely observe from Hilo for about 12 hours, 6 p.m. to 6 a.m. And then tomorrow we come up and we do it again. Yeah.